Okay, in this example, we're going to find the Thevenin equivalent of the circuit between points A and B. In other words, we're going to find the black box such that if you only had access to those terminals A and B and not to the rest of the circuit, you could not tell the difference between the original circuit and its Thevenin equivalent. To make this problem a little faster, I've already converted the circuit from the time domain into the frequency domain. Just as an aside, this weird diamond-shaped circuit is called a Wheatstone bridge, and it's useful because imagine that you've got a very long cable carrying a satellite feed that's represented by the 8 and the J12 ohm inductor on the bottom. It's possible to adjust that capacitor in the upper left to make the entire circuit look purely resistive. Now, we're not going to do it for this example, but I'm explaining a practical application of this when you might have a very long wire and you want to make it look purely resistive for reasons that'll be covered in an antennas class or an electromagnetics class. So let's begin. Our first step is to figure out which method of finding the Thevenin equivalent we want to use. Remember, there are three common ones. One is to find VOC and I short circuit. One is to find either VOC or ISC, and then zero the sources and do impedance simplification. And then the third way that you should only do if you've only got dependent sources is to put in a test current or test voltage and find the remaining voltage or current. The second way, finding either VOC or ISC and the equivalent impedance, is always the fastest. And so let's begin with that. Step one, find VOC or I short circuit. I look at this problem and I see two voltage dividers. I see a voltage divider on the left, composed of the left-sided capacitor and resistor, and I see a voltage divider on the right, with a right-sided resistor and inductor. So I know I can use a voltage divider equation to solve for this circuit, so I'm going to solve for VOC. I'm going to begin by redrawing the circuit using just vertical and horizontal lines like we're used to seeing. That will make the voltage divider more obvious too. Now our goal is to start off by finding VAB, which is the same thing as VOC, the voltage between the output terminals. So I'm going to label that. So there's our VOC, and we could solve for VOC by solving for all of the unknown voltages using nodal methods, or we could solve for it by finding all of the current flows everywhere using mesh methods, and then finding the voltage using Ohm's law. Clearly, since we're seeking to find voltages, we should use nodal methods. So let's begin with the nodal method. Our first step is to label ground. We'll call this unknown node VA. We'll call this unknown VB. And now once we find VA and VB, we found VOC. It's just the difference between the two. So we could set up nodal equations to find them, but it's even easier just to use the voltage divider equation. Do you see how VA is just that voltage divider? And similarly, we know the voltage across the rightmost two resistors, so we can do a voltage divider there too to find VB. When you do these, be careful to make sure that you know which impedance to put on the top. Since we want to find VA with respect to ground, our VA is really being measured here, as shown in red, and so we want to find the voltage across the 8 ohm resistor. Same thing for VB, we want to find the voltage between the top and the bottom of that J12 inductor, so that belongs in the numerator. All right, so now with our two equations written down, we plug them into our calculators, and now we can find our solution. VOC is equal to VA minus VB, and we've already found the parts from our earlier calculations. And this is one that you cannot do in your head. You can easily subtract two numbers in rectangular notation, but not in polar notation. In polar notation, you just have to put it in your calculator and get this. So that's the first step. Second step, and to find ZEQ, we will zero all of our sources, which means short voltage sources, open current sources, and find the impedance between points A and B. In other words, find out how hard it is to push current into A and pull it out of B. So here's our circuit redrawn with the sources zeroed out. Now, at first blush, it looks like none of these components are in series or in parallel. Remember, parallel means they're connected at the top and the bottom, so the voltages are guaranteed to be the same. And in series, it means all the current through one has to be the same as the current through the other. And you might think, well, this capacitor on the left and the resistor on the left, they look like they're in series because all the current that goes to the top would have to go through the bottom. But that's true if the current was being injected from the top, but it's not. We're looking for the impedance between points A and B. So we're pushing current into A and we're extracting it out of B. And when we're pushing it into A, actually the current splits between these two. So they're definitely not in series. If you look at this long enough, though, you can see something interesting, that this capacitor and this resistor actually are in parallel because they are connected at both ends. They're connected on this end, but they're also connected at that end. And we can make the same argument about the two components on the right. They're connected here, but they're also connected at the other lavender end. So all we need to do is somehow redraw this to make it clearer. And let me try my hand at redrawing it. I think you can agree that this is correct. And I think you can agree that these are connected. And the only thing that we're missing is a connection between these. And so the circuit on the right is the same thing as the circuit on the left. Let's just check that out. This 8 ohm on one side is connected to the 8 and the J6. This 8 ohm is on one side connected to the A and the J6. On the other side of this 8 ohm, it's connected to the other side of the minus J6 and both the 4 ohm and the inductor. On the other side of the 8 is connected to the other side of the capacitor and both the 4 ohm and the inductor. And we can do that with every piece. So the circuit on the right is the same as the circuit on the left. And now it's really clear to see that these two components are in parallel, these two are in parallel, and then there's a series combination between the two. Therefore, this is the formula for ZEQ, and the formula for parallel is product over sum, and product over sum. You place it into the calculator, and this is what turns out. And this is the ZEQ. Notice this, when we write sources, we write them in polar notation. But when we write impedances, we write it in rectangular notation. And that's because the polar notation helps us see what a source is in terms of a cosine. But the rectangular notation for the ZEQ shows us that we've got a real resistive part that looks like a 6.48 ohm resistor. And then we've got a negative J portion, which means that it looks like a capacitor. And this resistor is in series with the capacitor. So now we can finally write our answer. And that's our Thevenin equivalent. Now, you wouldn't be wrong if you wrote this source in rectangular notation, or if you wrote this impedance in phasor notation. It's just the standard to write it as I've done it. Why do we do it that way? It's because let's say we wanted to take it out of the frequency domain and put it into the time domain. It's easy to convert this phasor into the time domain. This one requires a little bit more thought. If we want to convert 6.48 minus J 2.64 into the time domain, that means into the real world of resistors, capacitors, and inductors, it should be pretty clear that the real part is going to be our resistor. And whenever we have a negative imaginary part, that's going to be a capacitor. If it was positive imaginary, it would be an inductor. To find out what the particular capacitance value is, we need to say that the impedance of that capacitor we know is equal to 1 over J omega C, which is the same thing as minus J over omega C. And we're not given our omega for this problem, and we're not given our capacitance either. So the best we can do is to say that this combination is equal to minus J 2.64. And if we want to solve for what particular capacitor we have, we can cancel out the minus J, and that leaves us with omega C is equal to 2.64. So our capacitor will be equal to 2.64 divided by whatever the circuit's omega is. And now, armed with that, we can write the entire time domain Thevenin transform. It would look like this. A 38 times a cosine, again, we weren't given our omega t, I'll just keep it generalized as omega t, minus 140 degrees. And that's our voltage source. And that would go through first a resistor of 6.48, and then a capacitor that would be 2.64 over whatever our frequency was. And this is our time domain Thevenin transform. Maybe now it's clear why we tend to write our ZEQs in rectangular format, because it makes it so easy to determine what's a resistor and what's a capacitor or an inductor.